Yeah. All right. We're gonna start a new section today. Is everybody ready? Let's turn the lights down. Get in that calculus mood. Put a little Barry White on. Y'all don't even listen to me anymore. Oh yeah. Okay. Y'all set? Everyone ready? Okay, we are starting section 3, chapter 4, and I hope to move into 4.4 today also. So now we're going to step away from what we did last section. Remember, last section was the mean value theorem. That was kind of a very special topic. Before that, we were doing absolute max and min of a function on a closed interval, but we had said that we want to eventually be able to find the max and min of a function if it's not on a closed interval. And this is going to lead us to that, all right? So, derivatives and the shapes of graphs. Remembering what it meant for a function to be increasing, decreasing, and constant. So remember, increasing means that as you move on the function from left to right, you're going up, right? Like if you're reading this function from left to right, or riding it like a roller coaster, you're going up, yes? Notice that if I take the slope of the tangent line, that green line, if I take the slope of the tangent line at any point, that the derivative, the slope, is positive. So when a function is increasing, the derivative must be positive for that to happen, right? It's going up, so the slope of the tangent line must be going up also. That's what the first note here says. If the derivative of the function is greater than 0, positive, on some interval AB, then the function f is increasing on that interval. Make sense? Yes? And then if it's decreasing, it's the opposite. You move from left to right, the function is going down. That means the slope of the tangent line there will be negative. So no surprises here. I hope that the picture explains what's happening. So if the derivative is negative on an interval, the original function is decreasing. So the derivative tells us about the shape of the function, doesn't it? The derivative is positive, the function shape is going up. If the derivative is negative, the function shape is going down. If the derivative is 0 on an interval, then we're looking at a constant function, right? That's what's happening. So look at this function. I'm having the computer calculate the derivative. So as I'm over here, it's increasing, right? When I get to the top, what's the derivative going to be? 0. And then once I keep moving to the right, the derivative is going to be negative. And then it's going to be 0, then positive. But also, this point right here is a local maximum, isn't it? Local maximum. And to the left of this, if I move a little to the left of that, my derivative is positive. If I move a little to the right of it, my derivative is negative. If I'm at the top, it's 0. So I wonder if that's what it's going to take for us to find where these max and mins happen. Are we going to have to look to see that our derivative goes from positive to negative? Does it make sense that if we can find where it goes from positive to negative, that we are potentially looking at a local maximum? Yeah? And then what about a local minimum? That's probably going to happen wherever our derivative switches from what? Negative to positive, right? That might connect us to the local min. So here's what the first derivative test says. There's two derivative, well, there's a first derivative test and a second derivative test. So this is the first one. Suppose C is a critical number of a continuous function. Okay, what does that mean? C is a critical number of a continuous function. Either the derivative is 0 there or the derivative is undefined there. Okay? So let's say that we have found a point in the domain of the function where the derivative is 0 or the derivative is undefined. Let's say that that's happening, okay? At this value c. Let's also say that the derivative changes from positive to negative at that point. So we're talking about like this right here. What's the derivative at this point right here? 0. So is that a critical number? Right here, somewhere down here on the x-axis, that's a critical number. To the left of it, it's positive. To the right, it's negative. This is saying if the derivative changes from positive to negative at c, then f has a local maximum there. If the derivative changes from negative to positive at that point, then it's a local minimum. If the derivative does not change signs, that means it goes positive to positive or negative to negative, then it's not a local max or a local min. So here's a picture. We have positive derivative here. There's a local max up there, right? Because it goes from positive to negative. So there's my maximum. Look at my derivative. It's negative. What about this point right here? What's my derivative right there? 0. To the right, my derivative is what? Negative. Is this a local max or min right here? No. Why? Because the derivative went from what? Negative to negative, right? It didn't switch signs. The first derivative test says we have to have a switching of signs in the derivative in order to have a local max or min. But over here, we go from a derivative being negative to what? Positive, right? Well, it goes through 0, but goes through 0. Doesn't want to go through 0. There. Goes through 0, and then it goes to positive. Do you all understand the first derivative test? Yes? You find the critical points, then you check to the left and to the right to see what the derivative is to the left and to the right of it. Understand? All right, now, some other things. This idea of what's called concavity, inflection points, and the second derivative test. So if a function f lies above all of its tangent lines on an interval, then f is called concave upward. What? If a function f lies below all of its tangent lines, then it is called concave downward. Okay, so let's try and understand what's happening here. Right here, my tangent line is here, right? The function is below it, isn't it? Yes? Is the function still below it? Is the function still below it? Right here, it's below, right? Here, it's still below. Now, I agree over here, it's not, right? But just looking in this little area, this little neighborhood right here, the red line is higher than the blue curve. Until I get to about where? Somewhere around here, right? Now, isn't my tangent line below the curve? Yes? Until I get to about here, and now my tangent line is above the curve. Until I get to about right here, and now I'm below again. So I hope you can see this, the red. Can you all see the red, then the green, then the red, then the green? Can you all see that? Okay, the red part of this is where my graph is concave down, because all the tangent lines are above it. The green part is where my graph is concave up. It looks like this, right? But only maybe one side of it. One side. And then over here, concave down, and then here to here, concave up. So concave down is concave down is like a frown, right? Sad face. Concave up is like a smile. Frown, smile. Yes? That's it. Where I have a frown and a smile meet. See where that frown and smile meet, where the cursor is? Where that frown and that smile come together? That point where it comes together is called an inflection point. That's what this note says. So first, what does it mean to be concave up and down? This gives us a way of determining where it is concave up and down. Look at what it says. If the second derivative is positive, your function is concave up. That's how we check to see if our function is smiling or frowning. We take the second derivative. If it's positive, it's concave up. Looks like a smile. If it is negative, second derivative is negative, then it is concave down. The point of the curve called the inflection point is where the smile and frown meet, which means that's where there's a change in sign of the second derivative, wherever your second derivative goes from positive to negative or negative to positive. Okay, so let's just back up for a second. What does the first derivative tell us about a function? Where it's going up and where it's going down, right? What does the second derivative tell us about the function? Where it looks like smiles and frowns, right? That's basically it. Now, the first derivative, you can actually use that to find local max and local mins. And the second derivative you can use to find what are called inflection points. Now, here's the second derivative test. Suppose the second derivative is continuous near C. All that means is that the second derivative, when you take the second derivative of the function, it's a good function. It's a nice function. So suppose the second derivative exists around some point. If the first derivative is 0 at that point and the second derivative is positive, you must be at a local minimum. Let's start with that. I have a curve, right? I tell you that at a certain point, the first derivative is 0. What does that mean? Slope of the tangent line is flat, right? Then I tell you that it's concave, what? What does this mean? Concave up, right? That's positive. Positive people smile, right? So concave up. So at some point, I have a flat tangent line, but the curve has to be concave up. That's got to be a local minimum. If the first derivative is 0 at some point, flat, but I'm concave down there, then it's got to be a local maximum. So here's the picture. My picture's too big. Hold on. Here's a point. Hey, the first derivative is 0 there. Hey, the second derivative is positive. Oh, then it must be that must be a local minimum, right? That makes sense? Same sort of logic here. Hey, there's a point. Hey, the derivative is 0 there. Hey, it's concave down there. Well, then that has to be a local max. So this second derivative test is a very quick way of finding local mins and max. But the drawback to it is that you have to take the second derivative, and sometimes that can be a pain in the butt. So there's two ways that we can find local maxes and mins. And notice I haven't said anything about a closed interval, have I? Okay? There's two ways we can do it. We can do it with the first derivative and look for where it goes up then down, or we can try the second derivative test. But we'll have to take the second derivative to do it. Understand? Let's do some examples. Am I recording? Yes, okay. So here's an example. This is for 4.3. Example, find where f of x equals 4x cubed plus 3x squared minus 6x plus 1 is increasing and decreasing. Then find local max and mins. Everyone got it? So when we say where is a function increasing or decreasing, like on this function right here, do you see the red? The red is where it's decreasing, right? If I ask you to tell me where it's decreasing, I mean what x value right here comes straight down. Between that x value and whatever x value is right here, between those x values is where the function's going down, right? So your answer to a question like where is it increasing and decreasing is going to be an interval. You're going to give the interval of where it's going up and the interval of where it's going down. Very, very good question. At 0, the function is flat. When we talk about decreasing, okay, in order to talk about decreasing, you have to be talking about 2 points. So let me try and give you a visualization of what I mean. If you have a graph that does this, that wasn't very good. You might think that at this point, it's not decreasing because the tangent line looks flat, but you have to be comparing it to another point next to it. The question is it higher than the point next to it, to the right? Is it higher than that point? Is that black dot above the one to the right of it? Yes. Isn't it? Because it looks like it's going down over here? Unless I drew a straight line segment. This curve looks like it's going down, then it flattens out for just 1 instant, and then it starts to dip down again. So to be decreasing means if I look at any 2 points, the one on the left is above the one on the right. And so even though the tangent line is flat there, it still qualifies that if I move to the right, I'm going down. Does that answer your question? Why are you back in the wheelchair? Crutches, okay. A little bit too much? Okay, I'm just curious. All right, I thought you re-injured yourself or something. Okay. All right, so you ready to do this? Okay, the place where it's increasing is wherever the derivative is positive, right? It's decreasing wherever the derivative is negative. So of course we're going to need a derivative. So we take the derivative. And this derivative, you really like this derivative, right? And so now I ask myself, when is it positive and when is it negative, right? So the easiest way to figure out where a function is positive and negative is to first figure out where it's 0. So tell me first where this function is 0. Where's the derivative 0? So set it to 0. You can factor a 6 out if you don't like that 6. And then I believe this quadratic factors 2x. Forgot to pull the 6 out of the middle, sorry. 2x what? Is that right? 2x squared plus 2x minus x minus 1. That should do it. So now, what are our solutions? 1/2 and -1. Yeah? Turn the lights back on. There, that's good. All right, this just tells me where the derivative is 0, right? Where the derivative is 0. So what I'm going to do now is I'm going to draw a number line. I'm going to put these 2 points on my number line. Make sure I put them in the appropriate order. What that does is that partitions the number line into 3 regions, right? So what I'd like to do now is I'd like to figure out what's happening in each of these 3 regions. I know that at -1, what's my derivative? What's the slope of the tangent line at -1? 0. What's the slope of the tangent line at 1/2? 0. So to the left of -1, is the derivative positive or negative? So I'm going to pick a test point, and it does not matter what point I pick as long as it's to the left of -1. Anything you want. How about -2? I'm going to pick a point between -1 and 1/2, something like 0. And then something to the right of 1/2, anything I want. How about 2? I'm going to take those 3 test points and plug them into the derivative, because I want to know what the sign of the derivative is, right? See, I'm not plugging it back into the original function, plugging them into the derivative. So below this, let's figure out what f prime of -2 is. So you have to plug -2 into this thing right here, the derivative. And all we care about is if it's positive or negative, right? So you can plug it in here, yes? Could you plug -2 in there? No problems, easy. Now I am going to choose to plug -2 into this right here, because that's still the derivative, right? But factored. I think for me it's easier to plug it in here. What would happen if I plug -2 in right there? You get -4 minus 1, -5, okay? -2 right here, -1. So I had what? -5 times -1, which is positive. 5 times 6, so it's a positive number, isn't it? It's positive. And I don't really even care what the actual value is. I just know that it's positive. So what that tells me here is that the derivative over here is positive, isn't it? Any number over here that I pick, this derivative should be positive. Then, the conclusion from that is that the original function there is increasing, right? Over there, it should be increasing. So the way that I use, the notation I use to let people know that it's increasing is just f with a little arrow going from left to right, going up. That's the notation that you can use in here to let me know that the function is increasing. Make sense? Now plug 0 in, do the same thing. 0 into here, I get negative, don't I? 0 into here, get positive. A negative times a positive is negative. Times 6, still negative. So that means that the derivative over here is less than 0, which means that the original function is decreasing. And then I plug in 2. And it's going to be positive. And that means the original function is increasing. Now, I've almost answered the first question. The first question was, find where the function is increasing and decreasing. So let's write the answer down. I'll squeeze it right in here. F is increasing where? So where was it going up? Over here, right? And over here. How do I say all the numbers out here forever, this direction? Negative infinity, all the way till I get to what? -1. Now the question would be now, do you include -1 or not? Technically you could, but our convention in this class is going to be that on every time we're talking about intervals of increasing and decreasing, we'll just use open intervals, so no brackets. It's not incorrect to leave out -1. Because like we said, you need 2 points to compare to talk about increase, decrease. So the fact that we're leaving out a single point is okay. Is that the only place it's increasing? No, it's also increasing from 1/2 out forever to the right. So we use the union symbol, 1/2 to infinity. That's where it's increasing. How about where it's decreasing? Where to where? That's happening in here, right? -1 to 1/2. Questions on that? Yes. You could. If it what? It would still be correct. Yep. But I recommend you just leave it out. Here's why. You might run into a problem later where that number's not in the domain of the function. Maybe it may not be in the domain of the original function. So then you're going to run into a problem. So since it's not wrong to leave it out and to just leave a parenthesis, just to be safe, you can just do that. Okay, questions? All right, let's answer the second part. Find the local maximums and minimums. Find the local maximums and minimums. So let's talk about what it would take to find the local max and min. And to do that, I'm going to go back to this. I'm going to go to that first derivative test. Suppose C is a critical number of a continuous function. Critical number meant somewhere where the derivative was what? 0 or did not exist. We didn't look at that, did we? For this problem? Not yet, right? But this says if we have a critical number and the derivative changes from positive to negative at that critical number, then it's a local max. If it goes from negative to positive, then it's a local min. If it doesn't change signs, then it's not a local max or min. That means if I come back to this little thing I drew, if -1 is a critical number, is -1 a critical number? Yes, because that's where the derivative was 0. Then it switches from positive to negative, right, as I move across here, then that should represent a local max. And then 1/2 was also a critical number, and it changes from negative to positive there. So that should be a local min. Do y'all see that? What I have not addressed yet, though, is the other types of critical numbers we could have had, where the derivative is what? Doesn't exist. But look at this derivative. It's a polynomial, right? The derivative is well behaved. It never doesn't exist. So the only two critical numbers we actually have are -1 and 1/2. So this should be the only local max. This should be the only local min. So without doing any more work, I'm going to say I have a local max. The local max is occurring at the point, where is it? -1. -1 is where it's happening, right? The x value. But remember with maxes and mins, I wanted to know like what the actual value was. You're going to have to take this -1 and plug it into what? The original. Correct. So plug into the original function -1, and that'll give you exactly where you are. So let's do that quickly. -4 plus 3, -1 plus 6, 5, 6. You should get 6 out of this. What about your local min? Oh, man. What are you going to have to do for local min? Plug in 1/2 into the original function. -1 was a little easier, wasn't it, to plug in? 1/2 might be a little more work, but I'll do it up here quickly. 1/2 cubed is 1/8, plus 3 times 1/2 squared is 1/4, minus 6 times 1/2, plus 1. So 1/2 plus 3/4 minus 3 plus 1. What is this? What do we get here? This is equal to, what's 1/2 plus 3/4? Same denominator, 2, 5/4. 5/4, and then these two numbers together was -2. But that's the same as 5/4 minus 8/4, getting a common denominator between these two, which is -3/4. Understand what I did? So -3/4. Done. Now, we're going to check it. So I'm going to graph it and verify it's x to the, wait, oops, no. Go ahead, 4x what? All right, there's the graph. It looks like, it's hard to see this. Looks like I have a local maximum happening at -1, 6, and a local minimum happening at 1/2. That looks like about -3/4, doesn't it? Also, where is it going up? As I move from left to right, it's going up, 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 up until I get to what? -1. Then it goes down from -1 to 1/2, and then it goes up from 1/2 the rest of the way. That all verifies my findings, right? All right, next example. Same questions. Find where f is increasing, where f is decreasing, and then find local max and mins. X over x squared plus 1. Let's look at it first. X over x squared plus 1. There's the graph. So what does it look like happens here? So I'm moving from left to right. It looks like it's decreasing, decreasing, decreasing. Looks like I'm going to hit a local minimum here, right? And then start going up, increasing, increasing until I get to what looks like a local maximum. And then it's going to come down again, right? Our results should match that. Let's see what happens. So what's the first thing you're going to do? Just find the derivative. How are you going to find this derivative? Quotient rule. Quotient, right? So derivative of the top times the bottom minus the derivative of the bottom. What's the derivative of the bottom? 2x times the top all over bottom squared. That good? Let's clean up the top. X squared plus 1 minus 2x squared all over x squared plus 1 squared, which is just 1 minus x squared over 1, or x squared plus 1 squared. That looks pretty clean, doesn't it? You happy with that derivative? All right, now, the critical numbers are critical, aren't they? I mean, in what we're going to do long term here. So how about we find the critical numbers? I know I need to set this equal to 0, right? But let's just write out what we're doing. Critical numbers, I'm going to set the derivative equal to 0. What do you have to worry about when you're setting this derivative equal to 0? Only the numerator, right? So 1 minus x squared equals 0, which gives you x's plus or minus 1. Two numbers, right? Positive and negative 1. You could have done that by difference of squares here. 1 plus x, 1 minus x, set them both equal to 0. Or you could have moved the x squared to the other side, did square root, did plus or minus on both sides. Either way, you're going to get two solutions. What about the derivative not existing? Is it possible for this not to exist? The only way that's going to happen is if you can get this to be 0. X squared plus 1 can't be 0 unless you have an imaginary number in there, right? 1 plus something squared can never be 0. So no issues here, right? Not applicable. Doesn't apply. No worries. Since, I'll just write this, since x squared plus 1 cannot be equal to 0. So I have my critical numbers. What am I going to do with these critical numbers? Make a number line. I have two critical numbers, so this will break up my number line into 3 regions. After I do this, plug in what? Plug what into the derivative? Test points. Test points. -2. 0 is a good one there. Pi. I could do pi, right? I'm not going to do pi. But I mean, I could, right? I mean, it just has to be to the right of 1. But you could use 10, you could use 1,000, doesn't matter. I thought it was supposed to be sunny today. That's what my thing said last night. It's supposed to be sunny. I heard it was supposed to rain tomorrow. They don't know anymore. They don't even know. They make how much money to stand up there and act like they know? That's right. It's a computer model, right? They're just trying to, what's that? Is that it? It's pretty sweet, man. All right. What is that, seriously? Oh. Okay. Gotcha. You need a couple more on that desk, man. All right, what now? Plug in? So I said I like to plug into the derivative. You know, there's different ways you can plug it in, like different versions. I think this is pretty clean right here, right? I mean, there's not a whole lot more I can do with this. Plug in -2. Notice I'm not showing the work, I'm doing it mentally. -2 right here. What's -2 squared? +4. 1 minus 4? Negative, right? So the top is negative. What can you tell me about the bottom? Doesn't matter what I plug in, does it? It's positive. It's something squared plus 1, all of that squared. It's positive. So I have a negative over a positive, which is negative. So my derivative is negative, which tells you that the original function is decreasing all the way till I get to -1, and then I plug in 0. Plug 0 in, you get 1 on top, which is positive, over positive, which is positive. So my derivative is positive here, which means my original function is increasing in between -1 and 1. And then I do the same thing for 2. And for that, I'll figure it's negative, and therefore it's decreasing. You notice that it switches, right? It goes from increasing, decreasing, then increasing, or it went from decreasing to increasing, then decreasing. Well, you hope it switches, right? It doesn't always switch, though. Okay, so you must be extremely careful to not just get the first one and be like, oh, they all switch after that, because you can get caught that way. It's not a good idea. You have to test the points. Okay, so this should be enough, right? We should be able to get this? Okay, the function is increasing where? Increasing. -1 to 1? The function is decreasing where? -infinity to... So I just did this on purpose. That's a mistake, right? Students will make this mistake. What did I do on accident? I used my test point as where it stopped. No, it's not the test point where you stop. It's the actual -1, right? So just be careful with that. All the way to -1, then after 1, right? That's where the function's increasing and decreasing. I also want to know the local max and local mins. So how about local max? Do I have a local max? At 1, right? Because look, it changes from positive to negative here. Positive to... Do you all see this like a hill? You go up, then down. I mean, that's got to be a max. Okay, so it happens at 1. That means you have to take 1 and plug it into the original function. So 1 into this is 1/2. Local minimum happens at -1, right? And now take -1, plug it into the original function, and we get -1/2. And that matches up pretty darn good with what we said we were going to expect to see, right? At 1, 1/2 is a max. At -1, -1/2 is a min. It was decreasing, then increasing, then decreasing, right? Pardon me? Are you going to what? You are going to start with the function and have to graph the whole thing on the test, which is the section after this one. You're going to start out with a function, and you're going to graph it all. So what we have not done right now, which we're going to get into, is, look, you can tell me where it's going up and down, can't you? In fact, you could, here's what you could tell me right now. You could tell me that at 1, you're up here at 1/2. You could tell me at -1, you're down here at -1/2. And that's about all you could tell me, other than it's decreasing and then increasing and then decreasing, right? How are you going to determine that this part looks like this? Well, there's a couple of things. It's concave up here, isn't it? Looks like a smile. That's going to involve the second derivative. Haven't even touched that yet. Also, this goes out and tapers out towards the x-axis because it has a horizontal asymptote. It's what happens when we take the limit as x goes to -infinity. And then the other side, we have concave down. It looks like a frown, but then it flattens out because we have a horizontal asymptote going that way. So when we get to the next section, sketching functions by hand using calculus, there's a whole slew of things we have to look at. Domain, vertical asymptotes, horizontal asymptotes, you know, first derivative, second derivative, concavity, all this stuff. We put it all together in one big picture. Hold on. All right, up to this point, the functions have been relatively nice. Derivatives have been pretty clean? Yes? All right. Same instructions. Same instructions. That almost looks like the exact same function, doesn't it? Except it's -1 instead of +1 in the bottom, right? So let's take a look at what's going to happen here. We're going to need the derivative first, right? So here's our derivative. Derivative of the top times the bottom. Here's the bottom. Minus derivative of the bottom times the top, all over the bottom squared. The top turns out to be -1 minus x squared over x squared minus 1 squared. That might have been too fast for you, I don't know, but I'm trusting you could do the quotient rule on this and get this, okay? Very similar derivative, right? Except we have a -1 instead of, we had a positive 1 there last time, didn't we? Yeah. All right, so let's find the critical numbers. So we have what? Where the derivative is 0. What do I need to look at? Just the numerator. Where is -1 minus x squared equals 0? Well, that's when -1 equals x squared, right? Just move your x squared to the other side. Is that possible? Not unless you have an imaginary number, right? So there's no solution here. We have no critical numbers that give us a derivative of 0. Understand? Is there anywhere where the derivative is undefined? Yes. That happens when the denominator equals 0. Where is that happening? X is equal to plus or minus 1. Right? You all still okay with this? So what am I going to do? Draw a number line. I'm going to put -1 and 1. I'm going to break up my number line to 3 sections. I'm going to pick test points. I'm going to plug these into the derivative. What's going to happen if I plug in -2? Negative on top. So now look what I'm doing. Instead of writing everything down, I'm just doing this. What is that telling you? My original function is going down there, right? Instead of writing the derivative is negative, f is going down, I'm just going to write an arrow going down so everyone understands that that means the function is decreasing there. What about 0? What happens when you plug in 0? Goes down again. What happens if you plug in 2? Goes down again. Understand? So, what's happening here? It's not a line. We're going to look at the graph. I wanted to wait because there's something else here that we want to talk about. But what can you tell me about, I'm asking you where it's increasing and decreasing. So where's the function increasing? Nowhere, right? Nowhere. How do you say that? How do you say the interval that actually is no interval? the empty set. That's not the number 0, it's the empty set. It's a 0 with a little kind of diagonal line through it. Means the empty set. That is the set that has nothing in it. That's proper notation for saying the interval of nothing. Where is it decreasing? Well, negative infinity, positive infinity? This is why I'm giving you this example. That's right. What's not defined? Negative 1 and 1, my derivative's not defined, but even more than that, the original function's not defined. That's the key. If the derivative wasn't defined there, that would be okay, because that might mean I just have a corner or a cusp or something. The fact that the original function is not defined at 1 or negative 1 means these numbers are not in the domain of the original function. So you can't tell me it's always decreasing from negative infinity to infinity, because that would imply that you mean it's decreasing at 1, but it's not even defined at 1. So what you have to do is you have to make that connection that these two values are not in the domain of the original function f. Therefore, it's going down from negative infinity to negative 1, union, negative 1 to 1, union, 1 to infinity. That's how we say in interval notation, everything except negative 1 and everything except 1. Is that notation okay for you? I always have students ask me, like, can I just write x can't be 1 and x can't be negative 1? That's correct also, but interval notation is preferred notation, I guess. The book, I believe, is going to use interval notation in the back. You want to look at this one? Just going to change that to a -1 down here. Recognize that? College algebra, rational function. You have two vertical asymptotes. So if I move from left to right, what happens? I'm going down, 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 down. Keep going down. But I have to pick up my pencil and come over here and then get on this side of the asymptote. And when I get on that side, I'm going to go down, 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 down. And I have to pick up my pencil and come over here and then do the same thing, down, 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 down. So the function's always decreasing. When you're on the function, it's decreasing. But there are two places you can't be on the function. Make sense? Yes? Here's a pretty classic example that I like to give. The function f of x equals 1 over x squared. Same questions. Where is it going up? Where is it going down? What are the local max, local min? Oh, we didn't answer local max min. Sorry. Local max min? There are none. You have to have the change, increase to decrease, to have local max min. Okay, what about this one? Take your derivative. I just did that because I rewrote the original function as x to the -2. And then I just did power rule. -2 came out, subtracted 1, got -3, and just dropped it back down. That's my derivative. What are my critical numbers? Where's the derivative 0? Only when the top is 0. Is the top ever 0? No. Because negative 2 can never be 0. How about the derivative not existing? At x equals 0, right? The bottom. So I draw a number line. I put here 0. Am I moving too fast or is this okay? Please respond. It's okay. A little fast? Okay. My derivative not existing is when the denominator was set equal to 0. X cubed equals 0 only happens when x is 0. I throw that critical number onto a number line, breaks it up into two regions. I pick two test points now. My test points are negative 1 and 1. These get plugged into the derivative. What happens when I plug negative 1 into this? Negative 1 cubed is negative 1. Negative 2 over negative 1 is positive 2. So what does that tell me my function is doing over here? Increasing, right? My function is increasing here. Now plug 1 in. 1 in there, we get 2 over negative 2 over positive 1, which is negative. So my function is decreasing there. Where is my function increasing? Negative infinity to 0. Where is my function decreasing? 0 to infinity. Questions? Local max. Do I have a local max? What are we looking for? We're looking for up to down, right? Do we have up to down? Yes, but you can't plug 0 into the original function. That's not in the domain. Suppose f is a critical number, right, of a continuous function. F changes from positive to negative at c, then it's a local maximum. Okay? If it's a continuous function, this is not a continuous function because at 0, because it has a break in the graph. All right? That's a critical point to make. Not a critical point. It is a critical. But anyway, that wasn't even supposed to be a joke, but I'm trying to make a point about the critical point being a critical point, literally and figuratively. All right. So this is a danger place for students. They see the up down and they're automatically swinging at it. That's a local max. You can't have it, right? Can't have it because it can't get plugged in. So local max, none. Since f of 0 is undefined. Your function has to be defined at the point. If you're going to tell me it's the highest point on the graph, you better be able to plug it in, right? And what about a local min? No, none. Since you never had down, then up. All right, very good. I would do it. I would just put a little explanation as to why. Yeah. I don't want you to, flip a coin on it. I mean, you know what I'm saying? I want it, if you can explain that you know. All right. One more example, and then we'll start talking second derivative. Here we go. Same questions. F of x equals x to the 2/3, 6 minus x to the 1/3. So let me make a little point here about what we've done up to this point. The first function we graphed was a polynomial function, which can be graphed in college algebra. The second one we did was a rational function, which can be graphed in college algebra. The third one we did was a rational function, which can be graphed in college algebra. And the last one we did was a rational function, which can be graphed in college algebra. This is neither of those. This is not a function you have ever looked at before. It's not exponential function, it's not a logarithmic function, it's not polynomial, it's not a rational function, not a line. So can we get an idea of how this thing behaves? Okay, so do you understand what I'm trying to point out here? That the other stuff was just to lead us into this. This is more of what a calculus student would be challenged with, trying to get a handle around what this is doing. Yes? Do you want to look at it first, or do you want to take a look at it first? Okay. Now, I've had some issues before with this thing graphing these properly. X to the 2/3 times 6 minus x, all of that to the 1/3, right? Yeah, it didn't do the negative part of it. Okay, so let me try something else. I'll bring in the big guns here. X to the 2/3 times 6 minus x to the 1/3. I've even had problems with this program doing it too. Well, this is Wolfram Alpha's brains. It's the way that I do this. X to 2/3. How about this? Let me try this. X to the 1/3 squared. Well, let's go with that. This is actually probably a good thing to see the limitation of the computer. I'm putting this in exactly the way it appears in the book. Yes. I think, if you type that in right. Yeah, it doesn't, I'm not having this part of it coming in. What do you mean?
Like right after the multiplication and right after the 1.
I don't know if that's going to do it. Well, I'll try. I don't think.
What was originally there on the left. Like change the left side back to the x to the 2/3.
Around this? Yeah. No. Sometimes these things are too smart for themselves. I'm not quite sure why this is limited like this. Okay, well, look, let's not get bogged down with it, okay? You have it on yours. I don't know why that one worked. You have it on yours also. Yours came up okay? Yep. Okay, so it looks something like, let me see it again. It's something like, does it curve down? Yeah, it does something like this, and then it comes back up and does something like this. Okay, that's what it does. Okay? So let's first take the derivative. I want to know where it's increasing and decreasing and stuff. Local max and min. So how are you going to do this derivative? Can you distribute this through the parentheses? I'm sorry? Yeah, product rule. I'm just making sure you're not going to try and do that because you can't do that because of the power here. If this power wasn't here, you'd be off to the races. You could distribute through and use power rule. But I can't, so I'm going to do product rule, which means derivative of the first one. What's the derivative of the first one? 2/3 x to the negative 1/3 times the second one plus the derivative of the second one is chain rule. 1/3 comes out, everything inside to the negative 2/3 times the derivative of what's inside of that, negative 1, times x to the 2/3, the first function. Wow, that looks nasty. All right, I'm going to try and rewrite this as clean as possible. I'm going to get like denominators, drop things into denominators. I'll have a 2, I'll have a 6 minus x to the 1/3. On the bottom, what do I have? There's a 3 down there, right? X to the 1/3. Plus, no, minus. X to the 2/3 over 3 times 6 minus x to the 2/3. So I drop this down with the 3 and then put this right here next to the 2. I use the fact that there was a minus here to bring that, change it to a negative. The 3 was on the bottom with this thing, and the x to 2/3 was up top. Yay! Now what? Because we have to set that to 0. Common denominator. Common denominator. Well, we have 3 in both. Yes. But I also need an x to the 1/3 in both. So I'm going to have to introduce times x to the 1/3 here, times x to the 1/3 here. Hey, that's going to work out pretty good. X to the 2/3 times x to the 1/3 is x to the 3/3, which is x to the 1, which is x. Right? X to the 2/3 times x to the 1/3 is x to the 3/3, which is x to the 1, which is just x. And then I have to get this right here on this one. So I'm going to multiply this by what? 6 minus x to the 2/3. I have to do that on the top also. Hey, and that's not so bad because 6 minus x to the 2/3 times 6 minus x to the 1/3 is 6 minus x to the 3/3, which is 6 minus x to the 1, which is just 6 minus x. Y'all with me now or no? Okay. All right, it just looks bad, but it's actually going to turn out to be okay. Okay, so putting this together with this, I get just 6 minus x. But then times 2, because there was a 2 there. So 12 minus 2x. That's going to be over the common denominator, right? Minus this, but this was just what? X. So how about I put these together now? Minus x all over the common denominator, which is, it's an ugly common denominator, but that's it. I can clean it up just a little bit. 12 minus 3x over all this stuff. Oh, we could have canceled a 3. Could have pulled out a factor of 3, couldn't we? But I won't. Are there any questions on how I got to this? All right. What next? Critical numbers, right? Critical numbers. So where's the derivative 0? Oh, well, that's pretty nice. 12 minus 3x is 0. That means x is 4. That's a critical number. What about where the derivative doesn't exist? Where is this thing going to be all messed up? 0 is going to cause division by 0. And 6. 6 minus 6 is 0. Understand? That's just by visual inspection. 0 here is going to make division by 0. 6 here is going to make division by 0. Number line? 0, 4, 6. That partitions my number line into 4 sections, which means I need 4 test points. -1, 2, 5, 7. And those numbers, I always circle my test points so that I don't confuse them with my actual critical numbers. I just kind of, that way I can distinguish between the two. I plug those numbers into the test points go to the derivative, right? Let's plug -1 in right here. What do you get on top? -1 right there. You get 50 positive, right? Over -1 right here. It's going to be positive to the 2/3 is positive, but then I'm plugging in -1 here also. What's the cube? This means cube root. What's the cube root of -1? -1. So we had 15 on top, positive in here, and then negative here. So it's negative. So it's going to go down here. Then we plug in 2. 2 up here is positive. Positive. Cube root of 2 is positive. So everything's positive. It goes up. And we plug in 5. 5 up top. Negative. 5 here. Positive. 5 here. Cube root of 5. Positive. So we should get, what, negative? And then finally plug in 7, and we should be positive. Are any of these points, do any of these critical points need to be thrown out because they are not in the domain of the original function? Original. Well, I had no problems up here, right? Like, I can plug anything number I want and do it to the 2/3 because that means what? The cube root of something squared? Cube root of something squared? This one right here, this is just cube root. I can do the cube root of any number. So there's no division by 0. There's no issues. So these critical numbers are all valid. So for trying to figure out where it's increase, decrease, I just need to look at these arrows. And then max and min, I'm just going to look for the changes. So where is this function increasing? 0 to 4, union, 6 to infinity. Where is it decreasing? -infinity to 0, 4 to 6. What about local max? Do we have a local max? What are we looking for local max? Change the sign going up, then down, right? So it's happening at 4. So that means I have to plug 4 into the function. Not so fun, is it? To plug 4 in here? It's 4 to the 2/3 times 2 to the 1/3, isn't it? That's what I would get if I plugged 4 in there. Sorry. Plug 4 in there for x. You get 4 to the 2/3. You plug in 4 in there. 6 minus 4 would give you 2, then to the 1/3, right? That's happening right here, the original function. And then you get on your calculator and figure out what that is to get a decimal. How about local min? We actually have 2 of them, don't we? At 0 and, and where else? 6. But what happens when we plug in 0 into the function? You get 0. What happens if you plug 6 into the function? You get 0 again. Plug 0 into here, 0 to any power 0, so that kills everything off. Plug 6 in right here, you get 0, that kills everything off. So those were easier to plug in. So what we did find, remember there's another side of this that comes up, right? There's another side of this that comes up. We found the local min here at 0, 0. We found the local max was at what? 4, and then some strange number. 3.17? Yeah, that looks good because that looks like about 3.17. 3.18. All right, we're going to have to settle it. No. Here we go. You're both wrong. 3.17480. Okay, all right, so we get the idea. And then the next one happens at what, 60? So this was a good example of where the graphing calculator actually, well, some graphing utilities actually fell short. Yes. Well, let me see.
It looks like there's like a little jump right there.
It's a vertical asymptote. I mean, not a vertical asymptote. It's a vertical tangent line. Look, remember the different scenarios that we could have where a derivative wouldn't exist? A derivative wouldn't exist at a corner, or a cusp, or a jump, or a vertical tangent, where you have something like this. Your tangent line has a positive slope, positive, 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 getting steeper and steeper. Vertical lines, the slope of vertical line is undefined. And then it comes back like this. Your calculator is freaking out at that point and trying to... Now, if you zoom in, it'll look like there's more there. But when your computer does these things, it doesn't graph every point. Was 7 negative? Well, let's go back, because I could have... Let's check 7. I'm being told it's negative. I think you're right. Let's try... Where is it? Derivative? 7 here is negative. Yes, 7 here. It's negative, but what does this mean? Cube root squared. That's a problem. This is negative. That totally eliminates 6 as being a what? Local min? Thank you for pointing that out. So change this. 7 is negative. Scrap your local min. Man, that changes everything. No, it changes your decreasing and increasing intervals. Doesn't it? I think I jumped the gun there too fast, didn't I? Yeah, don't make that mistake on the test. Okay, so what happens? How does this change our answer? Our increasing is now what? Just 0 to 4. Please adjust this. Our decreasing is negative infinity to 0, but then 4 to what? To infinity. Local max, does that change? Local min, there's just one. Sorry, I'm doing that because every once in a while it draws these like lines through my work and you can't tell what it is. See? Look. See? See? They said, son, telling you, it was supposed to be here. So do you all understand the basic concept here? All right. Homework, what? All right, we've got 15 minutes. I think we can probably do this. So there's something new here. We want to be able to find where a function's increasing and decreasing local max, mins. We've already done that, right? We know the process. But now I want to find this, and inflection points. So this means find where it is concave up. But that means I'm asking you to find where the second derivative is positive, right? This means I want to know where it's concave down, frowning, but that means just find where the second derivative is negative. The inflection points are where you have a change in what's called the concavity, where you go from concave up to concave down. Now, look at the way that we did the first derivative, right? We found the first derivative, we found the critical numbers, we did a number line, we broke up our interval, we did test points, and that told us if the function was going up and down, right? Right? This second part is the exact same process, except instead of working with the first derivative, we are going to be working with the second derivative. So everything we did with the first derivative, we have to repeat with the second derivative and make up our little test points. And then the only difference at the end, instead of saying it goes up and down, it's going to be smile or frown. That's the only change. So let's start this problem out. Start it out with first derivative. First derivative of this function is 15x squared minus 15x to the fourth. Very, very nice function, right? Well behaved. I would like to find the critical numbers. So I'm going to find where the derivative is 0. I'll do a GCF. right? Greatest common factor is 15x squared. Pull that 15x squared out. I'm remembering now why I'm so hungry. I went to go get the lunch out of the fridge today. My wife took it. She took it. It's like, I didn't eat lunch. Okay, 15x squared came out. This is what I'm left with now. Set everything to 0. Would you like difference of squares there? Or, it all depends on you how you want to solve this. I'm getting 3 solutions. 0, 1, -1. Yeah? The 15 doesn't matter, right? You could divide both sides by 15, it's gone. So what about where the derivative is undefined or doesn't exist? Any issues? No, that derivative's nice, right? Well-behaved polynomial, we're good. So I'm doing my number line. I'll just do it over here. -1, 0, 1. And we're going to plug in some test points, like -2, -1/2, 1/2, and 2. So I plug those into the derivative. Which means I can plug it into any version I had. I like this version right here. Why do I like that version so much? Right there. Because 15x squared is always positive, so that has no impact on anything, right? Let's got to figure out what these two are. So plug -2 in here. 1 minus -2 is +2, so that's positive, and then 1 minus 2 is negative, so we should get a negative when I plug in -2, which means my original function is going down. Then plug in a -1/2. I'm taking my time here. Yeah, done. Okay. So it's going, no, I'm kidding. So plug in -1/2. 1 minus a -1/2 is 1 plus a half. That's positive. 1 plus a -1/2 is 1 minus a half, so that's positive. So it's going up. Plug in 1/2. 1 minus a half, negative. 1 plus a half, positive. Negative times positive, negative, so it goes down. Plug in 2. What did I just say? 1 minus. Okay. I think I'm already Friday. I think it's Friday already for me. It's feeling like tomorrow I've got all these meetings too. I'm not looking forward to it. Okay, 1/2. 1 minus half. What did I say? 1 minus a half was -1/2 or negative? Is that what I said? Okay. 1 take away a half is a half. 1 plus a half is 1 1/2 or 3/2. So that's positive. So it does not change there. And then in 2, 1 minus 2 is negative. 1 plus 2 is positive. So that should be down, right? Where's the function increasing? -1 to 1. Do I have any problems with any of these numbers being not like in our domain? Any issues? No, because it was a polynomial, so no issues with that. So I can go -1 to 1. How about where it's going down? -infinity to -1, and then 1 to infinity. All right, max. Where do we get local max? Do we have a local max? At 1. Right? Goes from up to down at 1. So we plug 1 into the original function. 1 into here gives me 2. How about a minimum? It's that -1, right? Goes from down to up. So plug -1 in here. -5 and then negative, so -2. Okay, that's everything we did before, right? No difference. But now there's more. We want to know about concavity. So we're going to look at the second derivative and repeat the whole process. So what is the second derivative of this function? I don't know. I forgot what the first derivative was. Right here, this was the first derivative. So take the derivative of that. 30x minus 60x cubed. 30x minus 60x cubed. Then I find the critical numbers of this. That means I want to know when the second derivative is 0. Set that to 0. I think I'll factor out a 30x. Is that what I get when I pull out a 30x from here? And then set these equal to 0? So I know one answer is 0, right? From this, the only way that 30 times x can be 0 is if x is 0. This one, maybe you need to like write that out a little bit. Just solving an equation here. Take square root on both sides. Plus or minus 1 over root 2. Do square root on top and bottom. I have 3 critical numbers here, don't I? 0, positive and negative 1 over root 2. And also, you could have written it this way, root 2 over 2. You probably recognize 1 over root 2 is one of the common problems like from pre-cal. 1 over root 2 is the same as root 2 over 2. So you could do either way. Do I have any places where my second derivative does not exist? No, because second derivative is nice again, right? So I'm going to draw a number line again, putting 0, positive 1 over root 2, negative 1 over root 2. That breaks up my number line into 3 sections. And then I pick test points. I need to know where this number is, right? I need to actually know what the decimal is for this. Root 2 over 2. Negative root 2 over 2. In order for me to pick a number that's far enough to the left. So, and something in between here. So, what is it? 0.7. So, negative 0.7. So, anything to the left would work. Like negative 2 would work. But what about in here? Negative 0.5 or negative 1/2? Over here, 0.5 would work. And over here, 2 would work. So again, just getting that this is 0.707, something like that, approximately. And then you plug those in. You plug those into what? Second derivative. So in here. I think I'm going to look right here because I might be able to get this. See if I can do this. Negative 2. Right here. Negative 2 squared. 4. Right? Times 2 is 8. 1 minus 8. Negative 7. But I'm also plugging negative 2 in here, which gives me a negative 60. So I have a negative times a negative, which is positive, which means my function is concave up. So what I'm going to do is I'm going to draw a little smiley face. Right? Negative times negative is positive. So this is not increase, decrease anymore. Second derivative is concave up or down. Then I plug in negative 1/2. And I do the same thing. Negative 1/2 right here gives me negative 15. Negative 1/2 squared, positive 1/4. 2 times positive 1/4 is positive 1/2. 1 take away a half is positive half, and I had a negative out front. So it's a negative times a positive, which is negative, so I have concave down. Then I plug in positive 1/2. Positive 1/2 here gives me a positive number. Positive 1/2 here gives me positive again, if I do it in there. Right, because positive 1/2 is the same as negative 1/2. You're going to square it and get 1/4. Times 2 is going to give you 1/2. 1 minus a half is going to be a half. So this should be what? Positive. So concave up. And then finally plug in 2 into this. What do you get? Two here. 2 is positive here, right? 2 here would give us 1 minus the number, so it should be a negative out here. So down. That's it. Any problems with these points not being in the domain of the original function? No issues. So where is my function concave up? I like to put little arrows at the end of this. Where is it concave up? Negative infinity to negative 1 over root 2. Anywhere else? 0 to 1 over root 2. We're almost done. Where is it concave down? Negative 1 over root 2 to 0 union 1 over root 2 to infinity. Inflection points. Inflection points happen anywhere that there's a change in concavity. So we actually have 3 of them, don't we? It goes from smile to frown right here, then frown to smile, and then smile to frown. So all 3 of these points are inflection points. So you would have to plug them in. I'm out of time. You plug them in, and then the next one you'd plug in 0, get something, and then you plug in 1 over root 2 and get something. And where are you plugging those into? The original function. Okay? So pretty long problems and pretty drawn out, but I mean there's a method to them, right? Just kind of like do this, then this, and this, and this, and this. How critical is it going to be for you to get the derivative correct? Very critical, right? The original function here, 5x cubed minus 3x to the 5th. 5x cubed minus 3x to the 5th. There it is. So we had a local min, I hope at -1, -2, and a local max at 1, 2, decreasing all the way to -1, and then we decreased again after 1. We increased between -1 and 1. But look at the concave part. Where are we smiling? This is all part of a smile, isn't it? Until I get to about somewhere in here, and then that's where the smile meets the frown, right at the corner. And then it switches. So right in here somewhere. Where is that happening? Exactly at -1 over root 2. Okay, I need to let you go, but I'm sure you want something to do over the weekend. So page 223. It's still there. Clouds are in the way. 3, 5, 7. Where are those? Okay, there they are. 27, 29, 33, See how you do with it. So, 27 through 35, they want everything we just did. So 27, 29, 33, and 35 is everything we just did at the last problem. Concave up, concave down. Numbers 3, 5, and 7. Oh, they want everything else. Sorry. But on 27 through 35, they say to graph it on a computer to check to see if it verifies. You don't have to do that, but I encourage you to. I highlighted 5 and 35. Those involve trig functions, and they give you a closed interval, but do everything the same way. The only reason they give you a closed interval is so you have finite number of solutions. Viva Fiesta, I guess, right? Is it Fiesta start this weekend or no?